Often, we can't easily have or do something in real life. Maybe you really want a Lamborghini, but for various reasons can't afford one. But you can afford a scale model of a Lamborghini. With your model, you can admire the detailing and imagine driving around in the real thing. When we model something, we set up a system to experience it, to simulate what it might be like. Models are useful because we can try out different scenarios without having to do them in real life. For example, if you built a scale model of your school, you could try out all kinds of different scenarios. For instance, you could use your model to figure out the best location for a new parking area. If you tried out different parking areas in real life, it would cost a lot of money and be very disruptive. In mathematics, formulas are a kind of model. Formulas allow us to set up a system to play around with different scenarios. Growth and decay formulas are also mathematical models. They allow us to see how the number of things in a system increases or decreases over time. Graphs can help us see what the values are at different points in time, so we can better understand the nature of the growth or decay by modeling it. Growth and decay are important models to understand because they occur in so many different contexts. In biology, we can use them to study how a population multiplies over time. Or a farmer may wish to grow his business by dedicating 3 more acres to cultivation each year. In physics, we might be interested in calculating how long it takes for radioactive material to break down. In the world of finance, we might want to find out how much interest will accumulate on an account. In ecology, we might want to study how the water levels in Lake Powell dropped between the year 2000 and 2005. Or even in social media marketing, we can use growth and decay models to understand what it means when something goes viral on the internet. Growth and decay models are often described as linear, exponential, or logistic. The difference can be seen visually in graph form. Linear growth is a straight line. Exponential is a curve. And logistic is an S-shape. Growth or decay is linear if you are adding or subtracting the same value repeatedly over time. For example, say you are hiking up a mountain. You start out at 5,400 feet above sea level, and the summit is about 10,000 feet above sea level. You can use a graph to show exactly how many feet above sea level you are at any given time during the hike. The slope or steepness of the line on a linear graph is the rate of change. Linear growth has a positive slope on a graph, and linear decay has a negative slope. Rates are useful because they tell us how one type of measure relates to another kind of measure, like miles per gallon, dollars per pound, or beats per minute. In linear modeling, we can determine the slope of the line if we know the coordinates of just 2 points on a graph. And if we know the slope, then we know the rate. Our example graph shows how fast the hiker moved up the mountain. By dividing the hiker's change in altitude by the change in time, we can see that the hiker is ascending the mountain at a rate of 800 feet per 1 hour. Linear growth is based on repeated addition. In this example, 800 feet are added every hour. In other words, the rate of change is constant. Exponential growth is slightly more complicated because instead of repeated addition, it is based on repeated multiplication. In the world of math, we show repeated multiplication by using an exponent. For example, this is 4 raised by the exponent 2, which means 4 times 4. So with exponential growth, you have something being multiplied over time. Exponential growth is very powerful because you can start with a very small amount of something and in a very short amount of time, end up with a huge amount of something. Let's say we start with 4 bacterial cells. And then, 1 minute later, those bacteria divide into 2 and so on. How many bacteria will there be after 5 minutes? How about another 10 minutes? The answer is a lot. An exponential growth graph looks like this. You start out with a tiny amount of something and then shoot up to a huge number very quickly. So why isn't the world overflowing with bacteria? Because in real life, exponential growth and decay rarely proceed out of control like this. Which brings us to our third model, the logistic function. Let's revisit our bacteria in a more realistic setting. Say our bacteria are growing in a bottle of milk that has been left out in a warm room. The population of bacteria now has limiting factors. They have a set amount of food to feed on and are confined to the milk container. As before, the bacteria start out growing in an exponential way, but when they exhaust their food supply and fill their container, the population has reached its limit. It can't grow anymore. This is called logistic growth. When we graph this kind of growth, we see it as an S shape because the line levels out at the top. This leveling out is called the carrying capacity and is the maximum sustainable population in the given conditions. Mathematical modeling of growth and decay allows us to see what a complex process looks like over time. These kinds of models are powerful tools. They can help us visualize large-scale, real-world problems, like climate change, the effect of regional depletion of resources on a population, and economics issues that range from the simple, like production ups and downs in a manufacturing business, to the complex, like charting a global real estate bubble crisis. Mathematical models play a critical role in solving these kinds of problems. In this module, you will learn how to model linear and exponential growth and decay.